Hello everybody, welcome to BlueMarbleScience. Today we're going to listen to another Ballbusters episode, and this time they're going to try to teach us about pressure. Mostly you're going to hear from this guy.
Gas pressure, right? And like Nathan said, this is the single most devastating argument against the heliocentric spinning ball space monkey religion.
Oh, careful there, lapdog. We don't want to make the spinning space monkey mad now, do we? Tell you what, let's light this dumpster fire and have some fun. Quantum Eraser is going to kick things off with a discussion of Boyle's law, which he doesn't understand in the first place, but hey, why let that stop you? Let's let him belly flop his way through some of this, shall we? Warning! Please move out of punching range of your monitor. This is going to be classic.
Just gas pressure, that's it. It implodes the fallacy, model right at its core. The best part, that's not the best part. An incoherent first grader can stand against the premier physicist of the world and defeat any assault within seconds in between iterations of Candy Crush. That's how great this argument is, right? And it's very easy. So let's begin. We'll start off with Elmhurst University with the kinetic molecular theory explanation of Boyle's gas law.
Okay, I can't listen to this. Kinetic theory of an ideal gas, Boyle's law, which says the product of pressure and volume has to remain constant. In other words, if you cut the volume in half, the pressure has to double. Yep, we got it. What else you got?
It's over.
It's over? What's over? You just started.
So the necessary antecedents that cause gas pressure are simply, number one, the rapid motion and collisions of molecules. Collisions with what? Well, the walls of the container. This is quite elementary. Take either number one or number two away, and you don't have gas pressure. It's just that simple.
Kiwi, didn't you just say you can't have gas pressure without a container? Well, I don't see a container around that tank car. Uh-oh. What just happened?
No amount of linguistic or mathematical acrobatics will change it. By the way, newsflash, you can't have volume without a container. And we're going to get to that here in a bit. So say bye-bye now to your ball-tard spinning space monkey religion.
Not yet, Big Blue. I'll let you know when.
Okay,
Yep.
I mean, let's before we move on, let's relate this to Earth. So we're talking about the walls of a container and how that gives rise. What can you just repeat, John? The measurement that is applied.
Pounds per square inch, usually.
Force over unit area, either or. So you've got the measurement itself for gas pressure, the stuff we're breathing right now, or based upon the amount that presses or the frequency of pressing on the walls of a container. Now again, we've got our pretty graphic of where they allege we live, and across the entire surface there's gas pressure, high energy, and what's it doing? Well, it's just magically staying there. Well, no, that's what debunks the assertion that we are on anything like this graphic on screen right now, because the gas hasn't got a wall to press upon. Well, what's it next to? Well, it's next to a very, 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 very low pressure system. Near vacuum, in fact. So the gas, again, would fill the space because there's nothing for it to press upon. Only vacuum, a lower pressure system. And guess what? You don't press on vacuums, you disperse into them.
Well, we're going to do this experiment. The test rig is very simple. It's just a piece of pipe and an inclined manometer. And I'll go through more of that when we get away out in the shop in a few minutes and do this. But we want to use the scientific method for this experiment. And of course, we want to follow the requirements of that world-renowned physicist and grocery boy, Nathan Oakley. So let's do this thing. I have an observation. My ears pop when I drive up a mountain, and I can measure the change in atmospheric pressure on my cell phone. Aha, but I have an hypothesis. I'm pretty sure gravity is responsible for the atmospheric pressure, and I think that's what causes the pressure gradient. So we got to figure out a way to test this with some independent variables, one being the density of the gas in this open pipe, and the second being the height of the column of gas, because the density of the gas is going to allow us to measure the pressure in an open system without a container, and the height of the column is going to vary that amount of pressure to show us what the gradient would look like. Now, we also have to be able to analyze this stuff. So if our mathematical prediction of the pressure, considering all the gravitational effects and the laws of thermodynamics and entropy and so forth, come out equal to what we can measure out there in the shop, we can come to the conclusion that gravity really is the thing. So here are the calculations for what it should be, and I won't go through all of this in great detail. But basically, the difference in the densities of the two gases corrected for atmospheric pressure, because my elevation is about 900 feet, so we're not at 14.7 psi typically. Today it's running about 14.26. 27.7, for anybody that's wondering, is a correction to go from psi to inches of water gauge. And of course, the column height's the only other thing we need. So you can see the figures there. For a 12-inch gas column, we expect 0.014 inches water gauge. At 24 inches, 0.28, and at 38 inches, 0.45. So let's go do this. Piece of 1/2-inch pipe, which is 4 feet long. An incline manometer. And this thing reads air pressure simply by this red fluid that's in the tube. Right now, I'm going to reset this a little bit to show 0 pressure. Right there. And as you can see, got a valve on the bottom, but we're not really going to use it. And that thing may still have a little bit of butane in it, so let's just make sure. There we go. So 0 pressure up here. 0 pressure down there. There's no pressure in the system at all. I've marked the pipe at 12 inches, 24 inches down from the top, and I'm going to be setting this right here even with about the top of where that tubing is, because that's the height of the column of gas we're measuring. And then there's a final one at 36 inches, which is up here just sitting, well, it's actually 38 inches with everything just sitting up like that. So there's a 38-inch mark right there. Okay. I'll drop this back down. I'll let it just sit there for a minute. We're going to put butane in this pipe. And I found out the easiest way to do that is just through the tube. So, let me squirt a little bit of butane in here. Okay. You might actually be able to see the vapor come off the top. I need to keep this up at the same elevation. Let me let this, it's very cold when it goes in there. So let me let this just equalize just a little bit. Seems to be nice and full of butane. Now I'm going to connect the hose back to the high pressure side of the manometer. Make sure we're sitting on 0, and we are. Right on it. Now let's raise this pipe up to the point where we're at about 12 inches. More or less like that. Now you can see that the manometer is reading about 1 point. I'll call that 1.5 or 0.015. Let me get that right. 0.015 inches water gauge. Let's go to the next reading. At 2 feet. We're reading 0.03 inches water gauge. And now the final reading, I'll take the pipe all the way out of the vise. And now let's see what we're calling that. That looks like I'd say about 0.48. Let me put this back down to let's take this loose. Now, did we come back to 0? No, we didn't. Didn't quite come back to 0. So let's re-zero the instrument like that. One more time. 12 inches. It's about 0.013. Second one, it's about 24 inches. .026. And the final one, that shows 0.04. No, about 42. 0.042. Yeah, we came pretty close, pretty much back to 0 again. Actually slightly low. I'm gonna do one more time. And then we'll have 3 sets of numbers we can use. Go to 12 inches. One, 3 again. Two, 8. And the final one at 4.2 again. So there's our numbers. Now, get the gas out of it. 0. There you have it. Okay, well, here are the results. I've tabulated everything so we could see it very easily. Again, at 12 inches, we had predicted 014. We got 015, 013, and 013, so that's pretty close. 24 inches, we thought it should be 0.028. We got 0.03, 0.026, and 0.028. Again, very close. For 38 inches, we thought it should be 0.045. We got 048, 042, and 042. Still pretty good agreement. So you say we can't have gas pressure without a container? Sorry, buddy, that one's busted. So what do you think could have been responsible for the gas pressure and the gas pressure gradient that we just saw? Just think about it.
Gravity!
That's right, gravity. You know, you've seen gravitational acceleration. You can measure it yourself. You've seen gravitational lensing in 1919, 100 years ago. That was shown. Frame dragging was shown by Gravity Probe B. Time dilation was demonstrated in a satellite launch all the way back in the 60s. And Gravity Probe A did it as well. The perihelion precession of Mercury, the motion of the celestial bodies, including the discovery of Neptune, gravitational waves that are detected nowadays with LIGO. And what's your response to any of this? Nuh-uh. Come on, guys. Don't be an idiot. Things really start to get a little weird now. Quantum Eraser's third claim is just over the top stupid. He's going to explain volume, and his contention is essentially that a cup of flour is only a cup of flour while it's still in a measuring cup. He thinks if you pour it out on the table to make biscuits with it, it suddenly no longer has any volume. As he puts it, because you can't have volume without a container. Warning. Face palm oven mitts are suggested for this part of the debacle.
You see this part right here? We don't have to deal with pressure. You see this part right here? That's your huckleberry. You know why? Question. How can you have volume without a container? Back to the Balltards Wiki alma mater. Volume is the quantity of three-dimensional space enclosed by a closed surface. For example, the space that a substance, solid, liquid, gas, plasma, or shape occupies or contains. Volume is often quantified numerically using the SI-derived unit, the cubic meter. The volume of a container is generally understood to be the capacity of the container, i.e. the amount of fluid, gas, or liquid that the container could hold, rather than the amount of space the container itself displaces. So, in 3 sentences, we have container mentioned 6 times.
So I got a question for you, Kiwi. If I had a box of sand and it measured 1 foot by 1 foot by 1 foot, would you say it contained 1 cubic foot of sand? I'll give you a minute to work on the math. But while you're doing that, let me follow up with another question. If I poured that sand on the ground, would you say it's still 1 cubic foot of sand or not? Well, you betcha it's still a cubic foot of sand. Okay, Big Blue, your turn.
You'd still have to have that first part covered, which is the question, the main question. Where'd you get the gas pressure from in the first instance?
You mean like this, or maybe like this?
Bearing in mind, there's an assertion, and we'll put it on screen again just for comedic effect, that we've got a vacuum of space. So, given that that's the assertion, we would like to know where the pressure comes from in the first place.
Gravity, you moron.
Where's all this gas pressing on something in order to be gas pressure? That would need an answer first. But so we can move on and I don't hold John up any further. In this instance, we're in the a hypothetical situation that a globe head would actually concede to the fact that you've got to have something to press upon in the first instance. Then we move on, only then, to how you have a gas pressure gradient. Sorry to drag that out, but I thought that was necessary.
No, that's okay. Yeah. And like I said, it's a legitimate, I don't have a problem with this question because I asked that question myself immediately, right? But it's question number 2, not question number 1. So answer the first question, please. However, like I said, I was put under pressure, no pun intended, to answer this question. And like I said, it's a legitimate question, and it's even supported. Textbook of Medical Biochemistry. Thus, the diffusion of solute particles takes place down the concentration gradient. A pressure gradient with respect to partial pressure of gases. So basically, when you say the concentration gradient, you're saying it's synonymous with the pressure gradient. Same thing.
This is actually annoyingly funny. What this idiot is quoting from is the textbook of medical biochemistry. The sentence he's picked out is down toward the bottom of the first column. What the thing is talking about basically is respiratory exchange of gases. Oh, well, what the hell? It's quantum eraser after all. Lungs, kidneys, Earth's atmosphere. It's all the same thing, right?
What is the Earth? Well, it's a closed dynamic system. And when we talk about dynamic systems, we're talking about cycles. Now, does everyone remember back in high school what cycles there are, the main cycles, what cycles there are with gases in relation to the Earth? Now, everyone knows the carbon cycle, right? You get this. This exists. And most of the carbon, the CO2 cycle, is where does it originate from? Well, it's down here on the surface. That's where most of the gas pressure is. And then it's going to cycle itself, right? You get a lot of photosynthesis, both from marine photosynthesis and terrestrial photosynthesis, right? Everyone knows this cycle. So it's a cycle. In other words, you know this, guys, right? What's the next one? The nitrogen cycle. Same type of deal here, right? Most of the pressure is down or created on the surface, and it cycles. Too easy, right? What's the next one? Can anyone guess the next one on the panel?
Hydrological cycle.
The water cycle.
Right.
The hydrologic or the water cycle, exactly. So we're getting the same thing here, right? The cycles, this is a dynamic system. The Earth is a dynamic system. It is not a closed static system. That is the answer. So, I've answered this question for you. I shouldn't get this question anymore.
Well, if there was ever a train wreck, that was it. Let's see what we learned. You can't have pressure without a container. You can't have volume without a container. And our atmospheric pressure gradient comes from dandelions, fertilizer, and rain showers. Bullshit. I think that pretty much does it. Guys, thanks for watching. I really appreciate it. Don't forget to like and subscribe, and we'll see you on the next one.